All right, so we're going to go ahead and start working through our review here in preparation for the circuits test. You see here the list of things that you're expected to know. We'll spend a little bit of time going over the important concepts, and then in a separate video we'll do some practice problems. So let's start with some basic definitions of voltage, current, and resistance, which were the three new quantities that we really introduced in this particular unit. We'll start with voltage. So voltage really represents the energy of the electrons flowing through a circuit. The difference between a 1.5 volt battery and a 9 volt battery is that the 9 volt battery has a lot more energy. The electrons of that battery have a lot more energy. We sometimes will talk about voltage as being like height, okay? So I sometimes think about the battery as like lifting the electrons up to a height. So more voltage means more height, which ultimately is more energy. And we measure voltage in units of volts. Our next quantity here is current. Current represents the amount of charge or the number of electrons flowing through the circuit. We do have a formula for it. It's just charge over time. We'll talk about that in a second. But really, it's like the amount of traffic flowing through the circuit. And I think traffic's a great analogy for current. It's how many electrons are moving through. It is measured in units of amps. And lastly, we have resistance. Resistance represents how much a particular object impedes that flow of current through a circuit. So objects with more resistance will allow less current to flow through that particular circuit because they impede it, they get in the way more. And we measure resistance in units of ohms, which is the Greek letter omega, which looks like a horseshoe. All right, so let's go ahead and look at some of our basic equations that we use during this unit. So to start, we have Ohm's law, V equals IR, where V is our voltage, I is our current, and R is our resistance. We use that equation a lot during this unit. Up next, we have power equals voltage multiplied by current, P equals VI. Now, power is a quantity we actually talked about during the energy unit, our last unit. But it still is very relevant within our circuits unit. It's a measure of the energy per time measured in watts. And lastly, we have our definition of current. So current is the amount of charge per time. So we have I equals delta Q over T. And again, that just gives us the amount of current we have based off of our charge and our time. Let's move on then and talk about our voltage and current rule. So with voltage, we talk about loops, and our rule with that was the sum of the voltages for any loop through the circuit must equal the voltage of the battery. And if we think about voltage as height, that really makes sense, right? The battery lifts the electrons up to some height. They need to lose all of that height no matter what pathway they take to get back to the other side. So the voltage through any loop, the sum of the voltages must add up to the voltage of the battery. With current, we talk about our junction rule. The basic idea there is whatever current goes into a junction must equal the current leaving it. Okay, current doesn't disappear. There's no twilight zone here, so the current going in must equal the current leaving. Let's move on and talk about series and parallel circuits here. As a quick refresher, your series circuits are going to be circuits where the resistors are one after another. So a basic drawing of that would be we have the resistor there and then another one and so on. A parallel circuit, on the other hand, is when it branches and there's a bunch of different loops through the circuit basically. So it would look something like this. Those would be parallel resistors. All right, we're now going to talk about basic series and basic parallel circuits and how voltage, current, and resistance operate in those circuits. So in a series circuit, the voltages add up to the voltage of the battery, okay? So we can say, if we want to put an equation on it, we could say that the total voltage is just V1 plus V2 and so on, okay? They add up to that voltage of the battery. The current is the same for all resistors, okay? It's one single loop. There are no junctions, and so that current ends up being the same. And then the resistance, we have our basic formula that the resistance is just the sum of each individual resistor, which means that as we add resistors in series, it increases the total resistance. Moving on to parallel circuits. In parallel circuits, the voltage is the same for all resistors, okay? Each resistor in a parallel circuit is on its own separate loop, and so that means that it's going to be the same voltage across each individual one. The currents add up to the current of the battery. All right. And so we could, once again, if we wanted to put an equation on it, we could say that that total current, meaning the current through the battery, is just the sum of the individual currents. All right. And the resistors, when we add resistors in parallel, it decreases the total resistance. The equation we have is that 1 over RT equals 1 over R1 plus 1 over R2, and so on. All right, adding up each individual resistor. All right, so to finish off, we're going to talk about just some problem-solving tips for some of these more complicated circuits. So maybe we have something like this, where it's not quite a simple series or a simple parallel circuit. And so we're going to talk, and this is a fairly basic example, but I'm going to use this just as a example of the basic method. What we want to do is we first want to reduce this to a single resistor, find the total resistance of the circuit by looking for simple combinations. So I would see here that those two resistors are connected in parallel. I would find the resistance just of that parallel combination, and then of course we're going to redraw the circuit, okay, replacing that parallel combination with a single resistor here. All right, and then we go from there. We would just have a simple series circuit, and we basically break this down until we have one single resistor in our circuit. So we'd combine these two in series and replace it with this single resistor. Once we have that, we're going to find the total current or the total voltage through the circuit, and we're going to do that using Ohm's law, V equals IR. And from there, then, we're going to go and we're going to identify the voltage and current on the resistor and keep stepping that back, identifying the voltage and current on the resistors in the previous drawing, okay? Building our circuit back up until we have the voltage and current on each individual resistor. Okay, and that really just comes from using your voltage rules, using your current rules, and using Ohm's law, right? Once you have one of those, you can find the other. So if you know the voltage, you can find the current, and vice versa. Keep in mind that when you have two in series, like we do here, and they are combined, they're going to have the same current. They're going to get that full current, and then you can find the voltage of each. When you have two that are in parallel, like we do here, they're each going to get this full voltage, and you can find the current on each using Ohm's law.